Hey gang, it's me, Mr. Ellis. We're going to go through how to solve this dragster acceleration problem. All right, first, describe the motion of the dragster. Well, looks like it starts, I don't know, what would you call that, 30 meters? We'll call that, I don't know, west. The starting line. Going east. Let's see. Dragster passes. Starting line at about 1 second. And is slowing down. At 10 seconds, the dragster stops at 150 meters east of the starting line. Let's see, anything else? I don't think so. All right, next we want to draw a qualitative motion dot diagram with 5 dots and velocity and acceleration arrows. Well, the velocity is definitely to the east, and it's starting off fast, getting slower. Those look like 5 dots. I'm going to draw these arrows halfway to the next dot. My last dot has no arrow because the dragster has stopped. Which way is the acceleration? Well, if the dragster is going to the east and slowing down, that means the acceleration has to be to the west. So, I'll my acceleration arrows here to the west. Try my best to make them about the same length. There we go. All right. Number 3, determine the instantaneous velocity of the dragster at t equals 5 seconds. Hint, think of yesterday. Yesterday, we learned that the average velocity for a time interval equals the instantaneous velocity at the halfway time. So what that means is if I can find the average velocity for some time interval where 5 seconds is the halfway time, then I'll know the instantaneous velocity at 5 seconds. That jingling is my cat, so sorry about that. So, well, the interval from 0 to 10 seconds would have 5 seconds as a halfway point. So let's find the average velocity for that time interval. So number 4 here. Oh, didn't want to do that. So we're here, number 4. So average velocity is change in position over change in time. That's going to equal 150 minus negative 30 all over 10 minus 0. It looks like it's going to be 180 over 10, which equals 18 meters per second. And what that means is this is also the velocity at 5 seconds. So how is that going to help us do number 4, determine the dragster's acceleration? Well, over here, I'm going to go ahead and draw my velocity versus time graph here. Hey, we'll try that. Alright, so let's see. Let's make this a velocity in meters per second versus time in seconds. And what we know is that at 10 seconds, the velocity is 0. We know that at 5 seconds, like about right there, the velocity is 18. All this one right here, 18. So let's see if it'll let me draw a shape here in a different color. Let's do green. All right, so let's try this again here. 5 seconds, the velocity is 18. All right, the velocity of 10 there. There we go. We'll make that work. All right, so we know 2 points on this line now. So here's our velocity versus time graph. And if we know 2 points on the line, then we can calculate the slope. And the acceleration is just the slope. All right, so for number 4. We're still on number 4 here. So the acceleration equals the change in velocity over the change in time. So that's going to equal, let's see, a rise of 0 minus 18 over 10 minus 5. So it's negative 18 over 5, which is negative 3.6 meters per second per second. Okay, so write the dragster's equations of motion. We've got one already. We know the acceleration. We need to find the initial velocity to do anything else. So let's find the initial velocity. We know that v equals at plus vi. So we can plug in for a few items here to get the initial velocity. For instance, we can know that the final velocity is 0 at the time of 10 seconds. So the only thing we don't know is the initial velocity. And it looks like the initial velocity is going to be positive 36 meters per second, which matches pretty well over there with our graph. So pretty happy about that, pretty stoked. So that makes our velocity equation negative 3.6 t plus 36. And then the position equation, well, let's see, it's 1/2 the acceleration, so negative 1.8 t squared plus vi times t plus the initial position, which is negative 30. All right. Now, finally, when precisely does the dragster cross the finish line? Let's squeeze this in down here. So when the dragster passes the finish line, we said it was about 1 second earlier at the very top. So let's see if we can get a more precise answer. If he starts 30 meters to the west of the finish line, what is his displacement at the finish line? Well, it have to be positive 30 meters. So our strategy here is to use the special equation to find the dragster's velocity when it passes the finish line. And then we can use our equation of motion for velocity to find the time. So the special equation says v squared equals vi squared, so that's 36 squared plus 2 times the acceleration times delta x. So v squared then equals 1080. So remember, when we take the square root of any number, there's actually two answers. So that means v is going to equal plus or minus 32.86 meters per second. Which one of those are we going to use? Well, let's see. The velocity is always positive. The dragster is always going to the east. So we need to use the positive answer. And we're going to plug positive 32.86 into the velocity equation of motion to calculate the time. So when we do that, I'm going to skip a step in the algebra because I'm almost out of space. It's going to be 32.86 minus 36 all over the acceleration, which is negative 3.6. What's that going to equal? .872 seconds. Which looks pretty good because we guesstimated about 1 second up at the top. All right. Hope you had as much success with this. I'll talk to you next time.